What if, in the vast expanses of space, there are galaxies that are invisible to our eyes and instruments? Such structures, composed entirely of mysterious dark matter, may exist right now, yet their nature remains hidden from us. Modern scientific tools allow us to look further into space, but dark galaxies continue to elude us, as if concealed in the shadows of the universe. Meanwhile, distant exoplanets may harbor oceans filled with liquid water. Water is known to be a key element for sustaining life. But what conditions are necessary for its existence beyond Earth? Can we hope to find extraterrestrial life when considering the factors influencing the formation of such worlds? Or are we in for disappointment? Cosmology faces even greater mysteries, such as the existence of quantum wormholes connecting different parts of space-time. If these phenomena are real, they could fundamentally alter our understanding of the universe. But how might they interact with the more familiar structures around us? And what laws govern such portals into the unknown? The hypothesis of dark galaxies is one of the most intriguing assumptions in modern astrophysics. A dark galaxy is a hypothetical object of galactic scale that contains an extremely small number of stars, or is entirely devoid of them, which is the basis for its name. These galaxies are held together by dark matter, and may also contain gas and dust. To date, the existence of dark galaxies remains unconfirmed, despite the presence of potential candidates. What secrets do these potential dark galaxy candidates hold? And can they alter our understanding of the structure and evolution of the universe? E04502958 is an unusual quasar around which no galaxy has been detected. There is a suggestion that this object may represent a dark galaxy where the quasar has become active. However, subsequent observations indicate that a normal galaxy is likely present nearby. Virgo 21 was discovered in February 2005 and became the first convincing candidate for being a true dark galaxy. The object was identified during the study of hydrogen, Hi, radio emission at a wavelength of 21 centimeters. Its dynamics appear to be inconsistent with the predictions of modified Newtonian dynamics, MOND. Some researchers have hypothesized that Virgo 21 may be a dark galaxy and represent a tidal tail of the nearby galaxy M99, which is experiencing gravitational disturbances while entering the Virgo cluster. Dragonfly 44, discovered in 2015, stands out for its low brightness. It emits only 1% of the light that the Milky Way emits. This galaxy has an extremely low density. Its diameter is about 60,000 light-years, and the number of stars within it is less than 1 billion. In a study published in late August 2016, scientists calculated the mass of Dragonfly 44 by examining the velocity of stars and their clusters within the galaxy. The mass was found to be 1 trillion solar masses, which is close to the mass of the Milky Way, but only 0.01% of this mass is attributed to stars and gas. Thus, astronomers concluded that the galaxy is almost entirely composed of dark matter. However, new research from 2020 disproved this hypothesis. But if dark galaxies are indeed real, what other hidden structures or phenomena might exist in the depths of space? Can we hope to find similarly mysterious aquatic worlds on distant exoplanets that could offer new opportunities for discovering life? Water is a key element associated with the potential for life, and its presence on exoplanets is one of the main objectives of astronomical research. As the number of known exoplanets beyond our solar system increases, new horizons emerge in understanding their diversity and potential to support life. Authors of a recent study analyzed 17 Earth-like exoplanets, suggesting that vast oceans may exist on their surfaces, hidden beneath an icy crust. All these exoplanets are believed by scientists to possess geological activity and to be capable of cryovolcanism, implying the ejection of heated material to significant heights. 2 of these planets are located close enough to Earth that astronomers may be able to observe geysers on their surfaces using modern telescopes in the future. Over the past few decades, astronomers have described numerous exoplanets that vary in size, density, and distance from their stars. These planets can be divided into gas giants such as hot Jupiters, and cold Neptunes, as well as rocky exoplanets comparable to Earth. The latter are of particular interest, as they may harbor extraterrestrial life, especially those exoplanets that have oceans, planets containing significant volumes of liquid water. In a study published in the Astrophysical Journal, scientists assessed the internal heating and ocean depths on 17 icy worlds. The modeling showed that all of them are capable of containing large volumes of liquid water, consistent with their average temperatures and densities. However, new data indicate that the average temperature on these planets is 16 degrees lower than previously estimated. In particular, the exoplanets Proxima Centauri b and LHS 1140b, which have thin layers of ice, may exhibit cryovolcanic activity that exceeds that of Europa by hundreds of times. Additionally, research conducted with the James Webb Space Telescope, JWST, confirmed the existence of exoplanet K218b, which is likely to have liquid oceans. Data showing the presence of carbon-containing molecules in its atmosphere, such as methane and carbon dioxide, suggest the possibility of life. This exoplanet, 8.6 times more massive than Earth, lies within the habitable zone of its star, located 120 light-years away. Studies of K218b are intriguing because they may indicate the presence of conditions suitable for life. However, scientists caution against premature conclusions about the existence of life on this planet. Given its large size and structure, the planet may have high-pressure ice mantles and temperatures that are not conducive to life. Further research using the mid-infrared instrument, MIRI, aboard JWST, is expected to provide scientists with more information about the atmosphere of K218b and its potential to support life. Exoplanet research, as recent discoveries have shown, opens new opportunities for the search for extraterrestrial life, highlighting the importance of considering the diversity of exoplanetary systems in astronomical studies. How might the creation of a holographic wormhole using a quantum computer open new horizons for exploring oceans on exoplanets and understanding their potential habitability? Researchers have made a significant breakthrough in quantum physics by sending a signal through an artificially created wormhole for the first time in a laboratory setting. This wormhole, described by Albert Einstein and Nathan Rosen in 1935, acts as a tunnel connecting two points in space by utilizing additional dimensions. The foundation for this wormhole's creation lies in holograms made from quantum bits of information, or qubits, stored in tiny superconducting circuits. The researchers manipulated the qubits to transmit information through the wormhole. A team led by Maria Spiropoulou from the California Institute of Technology implemented a new wormhole teleportation protocol using Google's quantum computer, a device named Sycamore located at Google Quantum AI in Santa Barbara, California. This experiment emerged from a quantum gravity experiment on a chip, allowing Spiropoulou and her team to outpace competitors from IBM and Quantinuum. This experiment supports the holographic principle, which unifies two pillars of fundamental physics: quantum mechanics and general relativity. Since the 1930s, physicists have struggled to reconcile these two disparate theories. The former explains the behavior of atoms and subatomic particles, while the latter describes how matter and energy warp space-time, creating gravity. The holographic principle, which gained popularity in the 1990s, suggests a mathematical equivalence or duality between two structures. Proponents of this principle argue that the flexible space-time continuum described by general relativity is in fact a quantum system of concealed particles. Space-time and gravity emerge from quantum effects, similar to how a three-dimensional hologram projects a two-dimensional pattern. Although discussions about wormholes began nearly a century ago, it took many years to develop the theory and the effort of an experimental team to create the first wormhole on a quantum computer. The experiment confirms that controllable quantum effects in a quantum computer can produce a phenomenon expected in relativity theory, a wormhole. However, we cannot observe this wormhole like an ordinary hologram. While it can be considered a fiber of real spacetime, as noted by co-author Daniel Jafferis from Harvard University, it is not part of the reality in which we live or the reality of the Sycamore computer. The The holographic wormhole in the experiment consists of space-time distinct from that of our own universe. The question of whether this indicates that the space-time we inhabit is also holographic and formed from quantum bits remains open. Jaffris emphasizes that there is a possibility that gravity in our universe arises from quanta, akin to how this one-dimensional wormhole emerged from the sycamore chip, though this has yet to be proven. Research into the holographic wormhole is rooted in two seemingly unrelated papers published in 1935, one by Einstein and Rosen, the ER paper, and the other involving Podolsky, the EPR paper. In the ER paper, Einstein and Rosen derived the possibility of wormholes, seeking to unify general relativity with a theory of everything that encompasses both spacetime and its dependent subatomic particles. They turned to elements of the fabric of spacetime found by Carl Schwarzschild in 1916, shortly after Einstein's publication, which showed that mass can gravitationally collapse to the point of becoming infinitely concentrated. The singularities discussed by Einstein and Rosen are now known as points that we cannot describe or see, as they are hidden at the center of a black hole. They represent a domain where a quantum theory of gravity is required. Einstein and Rosen proposed that Schwarzschild's equations could be used to connect elementary particles with general relativity by replacing singularities with new variables and describing them as bridges between different parts of spacetime. Unfortunately, scientists did not initially pay attention to the phenomenon of quantum entanglement described in the EPR paper, which stated that measuring the state of one particle instantaneously affects the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein referred to it, became crucial in understanding quantum mechanics and holographic theory. In the 1990s, physicists discovered that quantum entanglement could enable new types of computation, leading quantum gravity researchers to consider it as a potential source code for the spacetime hologram. In a 1994 paper, Leonard Susskind articulated the holographic principle, suggesting that the volume of spacetime described by general relativity is equivalent to quantum particles at its boundary. Juan Maldacina's work in 1997 corroborated this principle by demonstrating that anti-de Sitter ADS space is indeed a hologram. Compared to our universe, ADS space is filled with negative energy and possesses hyperbolic geometry. Maldacina showed that gravity within ADS space corresponds to the properties of a quantum system at its edge. Subsequently, when Maldacina explored his ADS CFT correspondence, he discovered that the entangled particles corresponded to a hologram featuring a pair of black holes linked by a wormhole. A decade later, he concluded that this discovery might indicate a more general correspondence between quantum entanglement and connections through wormholes. In electronic correspondence with Susskind, they speculated that the Einstein-Rosen bridge between black holes is created by EPR-like correlations, and that this duality might be more general than previously assumed. Research also indicates that wormholes may link entangled pairs of particles throughout the universe, forming spatial connections that record their shared history. When Jaffris learned about Maldacina's work, he realized that such a duality should allow for the creation of individual wormholes by adapting the entanglement pattern. Previously, it was thought that Einstein-Rosen wormholes would quickly collapse under gravitational influence, but Jaffris proposed that a connection could be stretched between two entangled particles, opening a wormhole between them. Together with graduate student Pin Gao and researcher Aaron Wall, they confirmed that linking two entangled particles allows for operations that can lead to the creation of a traversable wormhole. The experiment conducted by Jaffris, Gao, and Wall in 2016 opened new horizons in the study of holographic mechanics. Later, Maldacina and colleagues developed a framework demonstrating that a traversable wormhole can indeed be created, confirming that quantum systems can generate and manipulate such phenomena. But how might quantum wormholes influence our understanding of the universe as a whole? Could vacuum energy, one of the most mysterious forces operating on cosmic scales, be related to these phenomena and unveil the secrets of the universe's expansion? Vacuum energy is one of the most enigmatic aspects of modern cosmology. It represents the sum of the energies of the lowest energy states of all quantized fields present in the vacuum. This energy exhibits uniformity in space and constancy in time, and its density is considered a universal constant. The existence of vacuum energy has significant implications that can be observed in various phenomena, such as spontaneous emission, the Casimir effect, and the Lamb shift. It is also believed that vacuum energy influences the behavior of the universe on cosmological scales. One prominent example of the observable influence of vacuum energy is the Casimir effect, predicted in 1948 by Dutch physicists H. Casimir and D. Polder. They discovered that a tiny attractive force arises between closely spaced metallic plates, caused by the resonance of vacuum energy in the space between these plates. This phenomenon has been experimentally confirmed and indicates that vacuum energy is real in the same sense as familiar conceptual objects like electrons and magnetic fields. However, alternative explanations for the Casimir effect have also been proposed. Other predictions related to vacuum energy are harder to verify. Vacuum fluctuations are always generated in the form of pairs of particles and antiparticles. Physicist Stephen Hawking explained the mechanism of black hole evaporation through the creation of these virtual particles near the event horizon. If one particle of the pair falls into the black hole, the other particle becomes real and is emitted into space. This loss of mass and energy is cumulative, which over time can lead to the disappearance of the black hole. The time required for this process depends on the mass of the black hole and can reach around 10 circumflex 100 years for solar mass black holes. Vacuum energy also has important implications for physical cosmology. According to general relativity, energy is equivalent to mass, and therefore if vacuum energy truly exists, it must exert a gravitational influence. A non-zero vacuum energy is expected to contribute to the cosmological constant, which in turn affects the expansion of the universe. But if vacuum energy does indeed influence cosmic expansion and other structures in space, what unusual circumstances led to the formation of stars? And how did they affect the development of subsequent cosmic objects? The very first stars in the universe formed approximately 300,000 years after the Big Bang, which corresponds to around 13.5 billion years ago. A recent discovery made by scientists from France and Italy using the VLT ground telescope located in Chile pertains not to the stars themselves, but to their remnants. In the early universe, heavy elements, known to astronomers as metals, were quite rare. The first stars were almost entirely composed of hydrogen and helium and had low metallicity. Throughout their short lives, nuclear fusion reactions occurred in the cores of these stars, transforming hydrogen and helium into heavier elements. At the end of their life cycles, these stars exploded as supernovae, contributing to the spread of new elements into space, such as carbon, oxygen, and magnesium, which have been detected in the outer layers of stars. All the elements produced by the first stars became the foundation for the formation of the next generation of stars, leading to increased metallicity in later stars due to the presence of more heavy elements. Scientists believe that the cores of the very first stars also contained a small amount of iron. However, the supernova explosions that marked the end of their life cycles were less powerful than those of modern stars. As a result, iron and other heavy chemical elements did not disperse far into space. Nevertheless, carbon mixed with iron, left over from the explosions of the first stars, has been detected in distant gas clouds. Researchers managed to identify this carbon in 3 scattered gas clouds containing remnants of the first stars that vanished billions of years ago. Astronomers are confident that this discovery will help deepen our understanding of the nature of the early universe and the character of the first supernova explosions. To find chemical traces of the first stars, scientists analyzed the light from the brightest objects in the universe, quasars. These light sources are formed as supermassive black holes, consume vast amounts of matter in the active cores of galaxies. As light passes through gas clouds, different chemical elements absorb it at various wavelengths, allowing researchers to determine the composition of the gas cloud. The analysis revealed that the clouds contain very little iron and a lot of carbon and other heavy elements produced from the deaths of the first stars. Scientists now plan to continue searching for similar gas clouds to ascertain how many exist in the universe. But if these giant primordial stars left their mark in history, how did the two mysterious substances, dark matter and antimatter, interact in those distant times? And what influence did they have on the subsequent structure of the universe? Scientists have discovered antinuclei composed of antimatter particles that have the largest mass among all known. Physicists have been able to confirm some theories regarding the nature of antimatter through the detection of the heaviest antinuclei made up of exotic elementary particles. This new discovery may aid in the search for the mysterious particles that make up dark matter. The research findings were published in the journal Nature, as reported by Science Alert. What is antimatter? The existence of antimatter was first recognized by physicists in 1932 when the positron, or anti-electron, was discovered. Since then, scientists have established that all known fundamental particles have their counterparts in the form of antimatter particles, referred to as antiparticles. Antiparticles differ from ordinary matter particles in that they have an opposite electric charge. It is believed that equal amounts of matter and antimatter were created during the Big Bang, but very little antimatter remains in the universe today. Physicists have been trying to understand the reasons for this phenomenon for decades, proposing various hypotheses. One such hypothesis suggests that almost all of the antimatter from our universe resides in an anti-universe created during the Big Bang. Returning to the new discovery made by physicists at the Relativistic Heavy Ion Collider in Brookhaven, USA, scientists collided the nuclei of heavy chemical elements at very high speeds in the collider. During these collisions, hundreds of new particles are generated, which physicists can identify. Most of these particles are pions or pi mesons, which exist for only fractions of a second before rapidly decaying. However, during the new experiment, physicists managed to identify the heaviest antimatter particle. In nature, atomic nuclei consist of protons and neutrons, but physicists can create hypernuclei, in which neutrons are replaced with a heavier version called hyperons. As a result, physicists discovered the heaviest known hypernucleus of antimatter, or antihypernucleus, composed of an antiproton, two antineutrons, and an antihyperon. This antihypernucleus has been named antihyperhydrogen 4. Physicists were able to identify a total of 16 such antimatter particles. Comparing antihypernuclei to hypernuclei showed that they possess identical properties: instability, decay in approximately 1/10 of a nanosecond, and the same mass. This supports existing theories. How is antimatter related to dark matter? Antimatter may be linked to the mysterious substance known as dark matter, which is estimated to be about 5 times more abundant in the universe than ordinary matter, yet has never been directly observed. Some physicists believe that collisions of dark matter particles may produce ordinary matter and antimatter, particularly resulting in particles such as antihydrogen and antihelium. Antihelium has already been detected on the International Space Station, which may be associated with dark matter. Experiments like those conducted by the US physicists will help better understand how much antimatter is produced in collisions of ordinary matter particles. This could bring scientists closer to understanding what constitutes dark matter and ultimately allow for its direct detection. If dark matter and antimatter indeed have a key influence on the universe, is it possible that there are cosmic singularities, mysterious regions where gravitational forces are so immense that time and space could break down? What role might singularities play in these processes? The cosmological singularity is a proposed state of the universe at the moment of the Big Bang, characterized by infinitely high density and temperature of matter. This phenomenon is considered one of the examples of gravitational singularities predicted by general relativity, GR, and some other theories of gravity. In 1967, Stephen Hawking rigorously proved the inevitability of the emergence of a cosmological singularity when tracing back in time any solution of GR that describes the dynamics of the expanding universe. However, this proof is limited to the framework of classical GR and does not account for quantum effects. Hawking also emphasized that observational results support the assumption that the universe originated at a specific moment in time. However, the very moment of creation, that is the singularity, does not obey known laws of physics. One of the problems associated with the cosmological singularity is the impossibility of simultaneously having infinite density and temperature. With infinite density, the measure of chaos approaches zero, which excludes the possibility of combining it with infinite temperature. The existence of the cosmological singularity is one of the most serious problems in physical cosmology, since any information about events after the singularity cannot provide insight into what happened before it. Attempts to resolve this problem are being pursued in several directions. Firstly, it is believed that quantum gravity could offer a description of the dynamics of the gravitational field free from singularities. Secondly, some researchers suggest that taking quantum effects into account in non-gravitational fields could violate the energy dominance condition on which Hawking's proof is based. Thirdly, there are modified theories of gravity in which singularity does not arise, as the extremely compressed matter begins to repel under the influence of gravitational forces, rather than attracting, as is assumed under singularity conditions. Another intriguing question is, what mechanisms, including gravitational lensing, can distort and amplify light traveling through cosmic spaces, and how do these processes unveil the mysteries of distant galaxies? Gravitational lensing is one of the most intriguing effects in the cosmos, resulting from the influence of large objects in the universe on light. However, this phenomenon can be caused not only by massive, but also by smaller cosmic bodies. The essence of the effect lies in the fact that light passing through another cosmic object on its way to an observer is distorted, altering the visibility of the light source. This distortion can be caused by stars or galaxies that the light from a more distant object passes through. There is also evidence that even small objects, such as planets, can cause lensing, although their impact is so minimal that it can only be detected using powerful telescopes. The discovery of the gravitational lensing effect was made possible only with the development of modern astronomy and the creation of advanced telescopes, which allowed scientists to observe and study this remarkable phenomenon. Light from distant objects such as quasars or galaxies is deflected as it passes through the gravitational field of another galaxy or star. This creates an effect similar to that of a lens, where the light is distorted and the shape of the light source changes. One of the most famous examples of gravitational lensing is the so-called Einstein ring. This effect occurs when the light from a distant object passes through a compact galaxy, becoming distorted and forming a circular shape. This phenomenon can be observed, for example, in the case of the galaxy cluster SDSS-J 1038 plus 4849, captured by the Hubble telescope. In this case, one galaxy acts as a lens for the light from another galaxy, creating the Einstein ring. Another variant of the gravitational lensing effect is the Einstein cross. It occurs when light passes through a spiral galaxy, creating an image reminiscent of a cross. This effect is also observed thanks to powerful optical telescopes such as the Herschel telescope, which in 2009 captured the object H142900028, a galaxy cluster that creates another Einstein ring. Gravitational lensing is a unique cosmic effect that allows us not only to study distant objects, but also to better understand the structure and interactions of various bodies in space. But if such forces can distort our view of the universe, what happens to objects that may simply disappear? Can an entire galaxy evaporate into the void of space if gravitational forces weaken? Although galaxies are considered some of the most massive and enduring structures in the universe, even they cannot exist forever. Sooner or later, they face an end. But what could lead to the demise of such grand cosmic objects? American astrophysicist Paul Sutter from the Flatiron Institute in New York provided an answer to this question in an interview with Space.com. According to the scientist, the quickest end for a galaxy may come from the activation of the supermassive black hole located at the center of most galaxies. For example, at the center of the Milky Way lies the black hole Sagittarius A*, which has a mass exceeding 4.5 billion suns. But what happens if this monstrous force starts actively consuming matter? In that case, the black hole will begin heating the surrounding gas to temperatures exceeding 1 billion degrees, releasing an enormous amount of radiation. This radiation will not only overheat the supplies of interstellar gas, but will also halt the birth of new stars permanently, or for a very long time.